Hello and welcome again to the Applied Business Statistics course. In the last lecture, we talked about simple linear regression. We gave an introduction to this topic and we finished with that the most important thing in simple linear regression model is to look at the residuals or error sum of squares, which is the most important thing which we finished with last lecture. So we have now one important criteria to discuss further and to build on. So we have the SSE, which we called error sum of squares or residual sum of squares. How do we use this? We want this error to be as small as possible. We need it to be the least error, the least possible error. So we want to have a straight line or a model that minimize this error, the sum of squares of the error sum of squares. We want to have this error to be the minimum, and we want to build on it. So we want to estimate beta naught and beta 1 using this error. So we want to have the value of beta naught and beta 1 that makes this error as small as possible, or the smallest possible value. So we have to make or to find the values of beta naught and beta 1 that makes the SSE minimum, or the least error possible. So this method of estimation of beta naught and beta 1 is called the method of least squares, or least squares method, in which we have the regression estimation technique that calculates beta hats, which is the beta naught hat and beta 1 hat, the estimates of beta naught and beta 1, so as to minimize SSE, the error sum of squares or residual sum of squares. So given the sample, no other straight line can produce a smaller SSE than the least squares or line. So this is because that we find the beta naught and beta 1 that makes the SSE the minimum, the least possible values. So the least squares techniques or estimators of beta naught and beta 1 without going the mathematical without going into the mathematical details. We don't need in this course to go through the mathematics, how to find the minimum values and these things. So we find the beta naught and beta 1 that makes the SSE the minimum, which are given where beta naught and beta 1 are given by beta 1 hat as SSXY divided by SSX, and beta 1 hat, the estimate of beta naught hat, the estimate of beta naught is y bar minus beta 1 hat, which we estimated earlier, this one multiplied by x bar. Now we xy is defined as this. This is the sum of squares. The sum of squares That's SSX. This one is SSX is the sum of the squares of the differences between all x values minus the average or the mean of x's and squared. So the squared values of the differences between the values and their means. So that's we call it SSX, the sum of squares of x's. And this mathematically can be if we square this value, that and enter the sum, this sum, we get this mathematically this expression, which is easier to use than this. That's easier to calculate. So this value equals this, which is the sum of all squared x's minus n times x bar squared, right? Then the SXY, which is equal this value over this value, and finally you will find it like that by using mathematics. We will find it like that: the sum of the sum of x, every value of x multiplied by every value of y, and we sum them, minus n, the number of observations, times x bar, which is the average of x values, minus the average y bar, which is the average of y values. So this is xy. We calculate it like that. We calculate it like that actually, and which is this value. So if we have these values which we need to calculate or to have at the beginning, then we calculate beta 1 hat very easily. Then if we have these two values, we calculate beta 1 hat easily like that. You divide this value over this value, we get beta 1 hat. Then also beta naught hat is easy to calculate, which is y bar minus beta 1 hat times x bar. That's easy. As long as we have x bar and y bar, then beta naught hat can be calculated or estimated very easily. So if we have these values, then we have the equation of the straight line, which is the simple linear regression model. That's the simple linear regression model, which we talked about on the previous lecture in the previous session. So the straight line or the simple regression model, simple linear regression model is y hat equals beta naught hat plus beta 1 hat times xi. That's the simple linear regression model, and that's all. Then, if we have an example, we can compute beta naught hat and beta 1 hat in it. The example says, after many hours of discussion with other more successful students, uh, Pat postulated a rather radical theory. That's a discussion between students, and they have a theory or belief that the longer one studied, the better one's grade. That means there is a positive relationship between hours of study and the student's grade in that subject, right? That's a belief or theory which we want to find. To test this theory, Pat took a random sample of 100 students, which is n number of observations here, in an economics subject, and asked each to report the average amount of time he or she studied economics and the final mark received. So each student among the 100 students is asked about how many hours studied economics and what are the grade in economics subjects to see whether there is a relationship between the hours studied in economics and the mark he or she got in economics also. So that theory suggests that study time determines final marks. So I mean, if we know someone studied 20 hours on economics, then we should expect his or her mark. Therefore, study time is the independent variable. Study time is the independent because the mark is the independent. So the study time affects the mark, not vice versa. Study time affects the mark, not vice versa. So the study time is the independent variable, and the mark is the dependent variable. So if we graph the paired observation, we have a scatter plot, a graph of the paired observation. The graphical techniques used to depict the relationship between two quantitative variables is called a scatter diagram or scatter plot sometimes. So if we have a scatter plot, then it will look or show the relationship between two numerical variables. So we have the independent variables is plotted in the horizontal axis usually, and the dependent variable is plotted in the vertical axis. This is the scatter plot which we learned in the introduction to statistics course. Scatter plot or scatter diagram. So for example, the scatter plot will look like this, which means that there is a strong relationship actually, and linear relationship and positive relationship. So that's this how the straight line looks like. So line of best fit by eye. This is the line of best fit by eye, but using the least squares techniques, which we described earlier, we'll see how does it look like. That's by eye, and there is a straight line which we fit using the method of least squares. The scatter diagram is the V's. What we can see as the things which I mentioned. Now, the things which I mean that the straight line model fits the data reasonably well. If the study time is zero, if for a student who doesn't study at all, study time is zero, then he gets a mark, not actually zero. He can get, for example, 5, 10, 20, and so on, but not highly more than 10, so more than 20. So around between 0 and 20, something like that, if he didn't study at all. Maybe he understands something from the lecture and he can write a few words and he got 5 marks out of 10, out of 100 actually. No one gets more than 100. So out of 100 he can get up to 10, up to 20 without studying at all. He did not pass the subject, but he gets some marks, not actually zero. That's the meaning of this value. The straight line does not pass through the origin, so if x is 0, y it's not necessary to be 0. If the study time is 0, then the final mark is around 20. The y-intercept of the line of the best fit is about 20. The third point, higher study times are usually accompanied by higher final mark. The higher the study mark, the study time, the higher the mark is. The higher the mark is. As he studied more, he gets higher mark, right? The line of the best fit is ascending. means that it has a positive gradient or a positive relationship. Positive gradient or positive relationship. تمام? So the line of best fit is ascending. There is an ascending relationship between the independent variable and the dependent variable. In this sample, there is a positive linear relationship between study time and final mark. This is what we get from the scatter plot, actually, without estimating the simple linear regression model. Now, the term now we want to estimate the simple linear regression model. So we have the sample regression line, which we calculate like that, as we mentioned earlier. We have n equals 100, and we assume that's an example. We assume that summation x, the sum of all x values without having the x values because they are 100 too much. So by Excel, we can calculate this summation x, the sum of all x values equals 2,795, and sum of y values 7,406, and the sum of squares of x values equals 86,239, and sum of multiplied x by y, multiplication by x by y, is 222,239, and these are the values are given without giving us the values of x and y, and we calculate SSX. We find it like that. This is the sum of x squared, which is that, minus n 100 x bar is the sum of x divided by 100, which is that value. So we square this sum of x, mean of x, average of x, we squared it and get it like that. The SSX equals then 8,118.75. That's the SSX. Now we want SSY also to be able to estimate beta naught and beta 1. So the SXY the same. We got the formula by this. This is the formula for calculating SXY, and the sum of multiplication x by y is like that, as we mentioned, minus n 100 times the summation x over n times summation x over 100, which is x bar and y bar. The results by calculation, the results of calculation is this value of 15,241.3. So we have these important two values. Then we can calculate the beta naught hat and beta 1 hat. First, we calculate beta 1 hat, which is equal this value over this value, and we get 1.877. And then beta naught hat equals y bar minus beta 1 hat x bar, and we get them like that, and we find beta naught hat equals 121.598. Right, and then we have the least squares sample regression. Least square sample linear regression model or linear regression line is y hat equals beta naught plus beta naught hat plus beta 1 hat times x, which is actually at 121.598 plus 1.877x. Using Excel, we get the same without formulas or anything. We get if we use the function of simple linear regression, linear regression, where we get these results by one function. Actually, we get all this result. This is the multiple R, which we will talk about later. That's the multiple correlation coefficient. Actually, that's R squared. This value is squared and adjusted. We will talk about them and the standard error of the regression, and observations are 100. Most important here now, up to now, are the values of beta naught hat and beta 1 hat. Beta naught hat is called the intercept, as we mentioned earlier. The intercept, that's the coefficient, that's beta naught hat. And study time, which is the coefficient of study time, which is beta 1 hat. The coefficient of study time, which is beta 1 hat. Study time is the independent variable. So its coefficient is beta 1 hat, which is beta 1. So we have this is beta naught hat, and this is beta 1 hat. So we can write down the the simple linear regression equation or model, which is beta naught hat or y hat equals beta naught hat plus beta 1 hat times x, which we're using these results, we get beta y hat equals 21.590 plus 1.877x. That's the equation of the straight line, which is the equation of the simple linear regression line, right? So the intercept of the coefficient, we calculate it like that, and we got it like that, which means that when x equals 0, that which is the study time is 0, which means study time is 0, the final mark is expected to be about 21.6. We mentioned error about 20, but here more exact value 21.6. If x equals 0, if student does not study or did not study any hour, did not study at all, then he will expect to have mark around 21, 22 or 21.6 without studying at all, maybe by attending the lectures only, right? And beta 1 hat, which means that for each additional hour of study, if you study 1 hour further more, if you study 1 hour more, then you get that value of the marks. So we get if we study 1 hour more, then we get about 2 marks. Exactly 1.877 marks, are about 2 marks. By studying 1 hour more, you get around 1.877 marks. So, and if you study more 2 hours, you will get about 3 something. If you study for 3 hours more, then you expected to get 5 marks more, right? That's the meaning of beta 1 hat, right? So this is the we have the the straight line fitted by hand, and this is the one which is fitted by the least squares technique, and which that's nearly rough or roughly the same, not different. That means this is the best straight line which can be fitted for these data. The best straight line which can be fitted by for that data. Why is the best? Because we use the least squares principle or the least squares criteria, which means that we get the values of beta naught and beta 1 that makes the sum of squares of the errors the minimum value. We make this error the minimum value, SE. We make SE the minimum value. That's why should be the least squares fitted line should be the best possible line for this data. The fitted line is ascending as we expected. So this is the best fitted line. This shows the fact. So now, after fitting the fitted line, so there are some things which we want to talk about as well, which we said that earlier we should said we'll talk about earlier later. We mentioned some points which and we said we will talk about them later. These are the R squared and these things. So that's the list squares lines the goes through the sample means here. That's the straight line which we fitted, right? Which is have this equation. The list square which have this equation, and that's the straight line. And we have y hat is better estimator of y than the sample mean y bar. So that's estimate of the y bar here, right? And this is a point here, x1, x1. If you have the value of x1, a point, then you expect to have the value of y1 here. So that's the estimate of y1, and that's why we call it y1 hat. In general, if this is any value xi here or here or whatever, xi, if we have the value of xi, you can predict the value of y like that. We get yi hat here. So given the value of xi, you expect or predict the value or the corresponding value of y, which is yi hat, right? And this is the error here. The difference between this value, if this is a value and this is straight line, so the value, the difference is yi minus y hat, y bar is the errors, which we usually take the square of it and sum all these errors, right? That's the error, yi hat, yi minus y I hat, and that's y hat minus y bar, right? So these are these errors which we use in the estimation of beta naught hat and beta 1 hat, these errors. And also, these values are very small, the smallest possible, and usually very small. If they are very small, then there is a stronger relationship between x and y. The smaller these values, the stronger the relationship. So we can use them also in having a measurement for the correlation between the independent and independent variable. This is a measure of how strong the relationship between the independent variable and the dependent variable. So this is we call actually the coefficient of determination, R squared. R squared. We use these errors to calculate or to estimate the coefficient of determination, R squared, which is the squared value of the correlation coefficient. The squared value of the correlation coefficient, but we here call it coefficient of determination. That's important value. Build upon the errors, those errors, and it has specific interpretation and very useful interpretation, which we should take care of. It measures the proportion of the total variation in Y, the proportion of the total variation in Y that can be explained by the estimated regression model. So the total variation explained by the independent variable. The total variation in the independent variable. How much effect of the independent variable on the dependent variable. The variation of the independent variables affect usually the variation in the dependent variable. So how much effect of the independent variable on the dependent variable, which is very important. For example, I know the study hour has great effect on the mark of the subject. Every one of us believes that the study hour has a great effect on the mark of the subject, but it's not the only factor affect the mark. So we do not expect that the effect of the study time has 100% of the variation in the marks of the subject, because there are other factors, like how much intelligent the student is, how much he study with peaceful mind or whatever. There are other factors. So how much explained in the variation of y by x is the r squared. Is the rest, if we say that it explains 70% of the variation in y, then the rest is 30%. This 30% is expected, or is due to unexpected factors or unmeasured factors, like intelligence or whatever. So the value of r squared give us how much effect of the independent variable on the dependent variable. The rest will be affected from the unexpected or unmeasured factors, right? So r squared has the following properties. First property of r squared is it goes between 0 and 1, or 0 and 100%. 100% is 1, right? R squared is not negative because it is squared value. Even if r is negative, then r squared is positive. R squared, any squared value cannot be negative. R can be negative, but r squared cannot be negative. Should be over equal or over 0 and less than 1, because also the correlation coefficient cannot be more than 1. Second thing is r squared can be 1. It is equal 1 if and only if. If and only if each observation is on the fitted line. If all observations are on the fitted line, then we expect r squared to be equals 1, which is complete or perfect fit. Perfect fit, no errors at all. All the errors are zeros. In this case, we will get r squared equals 1. So the independent variable in this case have 100% effect on the dependent variables. No other variables can affect the dependent variable except this variable. That's the meaning of r squared equals 1. And r squared equals 0 if and only if the model is completely useless. Completely useless. That means no effect at all of the independent variable on the dependent variable. No effect at all. And we say if and only if. That means exactly one to one. يعني. That means also and vice versa. Vice versa. The opposite is true. The opposite is true. R squared equals 0 if and only if the model is completely useless, which means also the vice versa if the model is completely useless, because there is no relationship at all between x and y, then we expect r squared to be 0. That's the meaning, right? Fourth thing, r squared is the measure of goodness of fit. How good is the straight line which we fitted? How good is the regression model, the regression equation, or the regression line, or the regression model? How good is it? If r squared is big, then the model is big or good. And the better the fit of the estimated model to the sample data, the closer r squared is to 1. The better the fit, the closer r squared is to 1. Right? That gives us measure of fit. Another point is that a useful computational formula for r squared is like that. We can calculate it like that. So we have xy squared divided by ssx multiplied by ssy. That we not mention the ssy. It is the same as ssx with substituting x by y, right? Which is like that. Similar to ssx actually. Ssy equals the sum of square difference between y and their average, and which is this formula similar to x actually. For an example 1D, calculate the coefficient of determination. So we can easily, using the above data, we can calculate the coefficient of determination r squared. So let us do it manually first. We calculated actually, we show it earlier using the Excel the results. The Excel results, we showed the value of r squared, but now we will do it manually. So we have already found ssx and ssx, but we also need to calculate ssy. Now, since sigma y equals 7,406 and sigma y y squared equal 584,518, then we can calculate SSY easily. And we get it like that, 36,029.64, right? And then we can calculate r squared like that. We get it. We get earlier the xy, which was 15,241.3. We square this value, and then are multiply x by xy, and we get the result like that, 0.794, which means 79%. 79%. That means the study time describe only 79% of the mark of that subject. and there is 21% of the mark in that subject is explained by other factors like intelligence or whatever. But on the study time only explains differences or the changes in the marks in that subject is explained by the study time. 79% of the change in the marks of that subject is explained by study time, and the rest is explained by other variables or other factors, right? With Excel, we have got it earlier, and we got it like that. That's the multiple correlation coefficient and ordinal correlation coefficient because it is simple linear regression, and R squared, which is exactly like that. R squared. There is another formula for adjusted R squared, which is not very big difference between them. And that's the standard error of the model, and we have an observation. So this is the R squared without going through these formulas. Using the Excel sheet, we can find R squared easily using the simple linear regression function in Excel. So this suggests that about 79% of the total variation in the final marks can be explained or is due to the variation in the study time. The remaining 21% is unexplained because it is explained by other factors. It is explained by other factors or other variables. Right? Now the square root of R squared, which is the sample correlation coefficient. So the sample R squared is the sample coefficient of determination, and the R is the sample correlation coefficient. The square root of the R squared is the Pearson correlation coefficient or coefficient of correlation. So R is the sample correlation coefficient. R squared is the coefficient of determination, sample coefficient of determination between the observed and estimated Y values. Right? In general, the sample correlation coefficient are measure the strength of linear association between two variables in the sample. The correlation coefficient we know from the introduction to statistics course that this measure the strength of linear association or correlation between two variables in a sample. Right? It has the following properties. That's the correlation coefficient. It is between -1 and +1. It can be negative and can be -1, which indicates that there is a perfect correlation, a perfect relation, but negative linear relationship between the variable. So in general, if it is minus, if the correlation coefficient is negative, then the relationship between the variables is negative. Observation are on a straight line. In that case, if it is exactly -1, so the observation are on a straight line, sloping downward. The straight line going, so sloping downward. If it is exactly +1, then as we mentioned, indicates that the perfect positive relationship between x and y. So all observations are on a single straight line sloping upward, right? So the other last thing is R equals 0 suggests that there is no relationship between the two variables. When R equals 0, that means that there is no relationship between the variables And also the sign of R, as we mentioned earlier, shows what the nature of the relationship, whether it is positive or negative, and usually R is between -1 and +1. The closer to 1 or -1, the stronger the relationship between X and Y is. So the stronger is the relationship between the variables. So in the example using Excel sheet, we calculate the sample correlation coefficient between X and Y here, and usually we can, if we have the R squared, then we calculated manually actually, which was like that, and we calculate R squared manually, and we can calculate R manually, just it is because the square root of R squared. And using Excel sheet also, R squared is that, and R is that, which is the same as here, the same exactly. So there is a reasonable strong association, for example, between the observed and the estimated Y variables, which means strong association between the study time and the marks students get in economics. So in the context of regression, R squared is a more useful statistic than R, since R squared measure the proportion of the variation in Y that can be explained by the regression model, can be interpreted precisely better than R. So we can rely on the interpretation of R squared better than relying on the interpretation of the ordinary correlation coefficient R, right?